The focus today is those small field tools. So of course the single detectors are a big part of that, our diodes, our scintillators, and of course the small ion chambers. But we have 2D detector options and phantoms as well that I'd like to touch on, because those are also, in my mind at least, a critical part of your small field toolkit. So for the single detectors, really when you're looking at detectors, different types of detectors, what we've got is that established technology in the diodes, although diodes, as most of you know, I hope most of you know, have some perturbation issues just because of the density differences that exist within the materials that are used for those diodes. We have newer technology. I guess it's been on the market for a while now, although it's still fairly new to a lot of people. And that is the scintillators, the X-ray W1 and W2. And then with the ion chambers, that's kind of an old standard. It's really the fallback for everything that we've done in dosimetry for so long. But it's, I would say, finally working properly in miniature form, and there is some data to back that up with our X-ray and A26. So I'll talk about that as well. So those are the focuses here for the single detector. What I'd like you to keep in mind as I'm going through this, or as you're looking through even our competitors' websites, looking at other people's detectors, every detector that you'll find has both strengths and limitations. And I will be completely honest with you. I'm going to present both for our detectors. I want you to do good physics. So I want to talk about these in a very open and honest sort of way. That's really the way I operate. So the best solution that you're going to find for your small fields really is a good combination of detectors, so that those strengths can play together to counteract the limitations that exist. So with the diodes, our diodes are called the D1V and the D1H, and the V and the H really only refer to the orientation of the stem on these. The same diode is used in both configurations. So the behavior is exactly the same between the two. Really, the difference is that vertical orientation is for scanning, so that you have minimized the perturbation of the water as you're moving through the scan, and as well as stem being there in the field. And the horizontal orientation is an easier one to mill out a solid phantom for. And so that's really designed for use in solid phantoms. But either one can be used either way, whatever works best with your setup. The diode that we use has a 1 millimeter diameter, so spot size. You'll hear me use that term spot size. That really is the area that's encompassed by the detector itself. This has an impact on the field sizes that you can measure because of the lateral scatter equilibrium or lack of equilibrium that you might run into. But it helps us really put all of these detectors into context in terms of the volume averaging that occurs across the fields. There are correction factors that have been published for our diodes. There were 2 publications in 2014 in particular that looked at both measured and calculated factors. This image here is taken from one of those from Papakonstantopoulos et al. But those are, I think, good references if you are using our diodes for the small fields. Another image here. Whoops, sorry, I'm showing my mouse on the wrong screen. Another image here with from publication from Paulo Francescan, also 2014, showing our diode here in green with the scintillator here in red, but being close to unity, but still, of course, having some corrections that are required in those small fields, just due to the density of the diode material itself. So strengths of diodes, as you're comparing your detectors, strengths of diodes are that they are very much a well-established technology. They've been on the market for quite some time. We kind of understand the radiation damage, the behavior, the energy dependence of these detectors. They give a nice high quick signal, so you can use them for scanning very easily. No bias, of course. They provide minimal volume averaging because we get that higher signal. You can use that smaller detector area still get a nice high signal. And our diodes have a low angular dependence for these types of applications. There is an angular dependence. You'll find that with pretty much all diodes, again, because of the densities, because of the way they operate. But as long as you are using diodes in really the orientation or near orientation that they were designed for, that's something that doesn't really play into it as much. Limitations of diodes, I guess I've brought some of these up already. They're not water equivalent, really just because of the materials that are used for these diodes. So there are corrections required as your beam quality changes or as you get down into these small fields, like is defined in some of the small field protocols. Or described, I should say, the spectrum changes just because of the shielding of the source and because of the way the collimation affects the field shape. So those corrections really are applied. And as I mentioned, there is some angular dependence with our diode if you were really to get around to the side or down close to the stem as you're irradiating these. The next detector I want to touch on is the scintillation detectors. We have two, the W1 and the W2. Both have the same active material, same fiber, same sort of construction of the portion that's in the field. So it is an organic scintillating material. Depending on what you're using, that might be a 1 millimeter by 1 millimeter active region, or for the W1 and the W2 1x3s, it's a 1 millimeter diameter, 3 millimeter long active scintillation region. The organic scintillator, as well as the plastic fiber that we use for transmitting the optical signal, is water equivalent. But the tricky part with scintillators is that you do have to correct for the Cherenkov light that is produced when you irradiate that optical transfer fiber. It manifests really as stem effect signal. So we have a method for removing that extra signal from your measurement, so you can get back just the signal you've measured from the scintillator at the tip of the fiber. They're also a type of detector that does decrease in signal as you give it dose, so it needs a periodic recalibration. You can get output in terms of dose if you deliver a reference dose to it. It's really just a conversion at that point from the measured signal to the dose that you'd be reporting or that's being measured. But it's not something that you can send off to the calibration lab and have it remain stable over a couple of years, just like a diode. It will decrease signal slightly as it receives higher doses of radiation. The way our Cherenkov correction works is that we use a 2-channel chromatic correction. And I deleted the reference there, but oh dear, and now I've forgotten the name. I will find the reference and include it in the email. Oh dear, that's going to bother me. Anyhow, we're using this 2-color chromatic correction. Our scintillator is a blue scintillator, and so the majority of the signal falls into kind of that blue portion of the spectrum. The Cherenkov is a broad spectrum light, so it falls into both what we call the blue portion of the spectrum and the green portion. And if we make a couple of measurements where you keep the dose to the scintillating volume the same, and change the amount of optical fiber in the field, you can alter this spectrum such that only the Cherenkov contribution is changed. So you get an increase in signal in both channels, but it's due only to the Cherenkov signal. And from that change in the blue signal between what we call the maximum configuration and the minimum fiber configuration, relative to the change in the green channel, we can determine that relationship between the magnitude of signal in the green channel to the magnitude of Cherenkov in the blue channel. And then with that, we call it Cherenkov light ratio, you can correct subsequent measurements by subtracting the value from the green signal times that Cherenkov light ratio from the blue signal to get you back your original scintillator signal. There was a question that came up, I just noticed, about how do we change the length of the scintillator? That's in the construction. When we make the fiber, we either put a 1 millimeter piece of scintillation fiber at the end of the optical fiber, or a 3 millimeter long piece. It's a 1 millimeter diameter optic or organic scintillator that we're cutting and polishing to be the right size. So with the characterization measurements here, that gets you your output in terms of the optical signal, which then is converted to a charge measurement through the optics that we have, the photodiodes. You can also perform that dose calibration that I mentioned by giving it a known dose in a reference field size. And that really then is applied as a scaling factor on this calculation here to convert from the charge collected to dose. So with the W1 scintillator, that was the original device that we developed. It's a 1 millimeter diameter, 3 millimeter long active scintillation region attached to that PMMA optical fiber. It's been on the market for a while now, so there are a fair number of publications about the W1. One of my favorites is the small field protocol that was the joint publication from the AAPM and the IAEA, which lists the W1 with a KQ of 1 for every table it shows up in, all the field size it shows up in. And this really is a testament to the water equivalence of the detector. The change in the spectrum, the change in the beam quality that happens as the field sizes are collimated down doesn't affect the response because this is a water equivalent plastic. I would point out, I guess, that if you're looking at the protocol, it is good to be aware that that the places where data are not shown for some of these detectors, the uncertainty or the variation in the measurements were high enough that the committee felt that it was not appropriate to use the detector in those fields. So strengths of the W1 is that KQ of 1, really, the water equivalence manifested in that calculation as well. But it is water equivalent for both megavoltage photons and electrons. So you can use it across the range of therapeutic energies that way. We're not observing dose rate or energy dependence with this detector, really, because of that water equivalence as well. There is a very small but negligible temperature dependence. If you're performing all of your measurements at room temperature as calibration, near calibration temperature, then that doesn't need to be accounted for. It really is about 0.1% per degree Celsius. If at some point we move towards an on-patient sort of measurement, then there may need to be a temperature correction then. But for your QA, for your output factor measurements, all of that, you can ignore the effects of temperature and pressure, of course, because there's no air in this to be affected by changes in the air pressure. Limitations of the W1 is that this really was a point detector. It was not designed for scanning. It's also a small field detector, so it's not designed really to operate in the very large fields. It has a low signal to noise ratio, so there's a much higher uncertainty in your measurements as you get out of the field. If you were trying to do a point by point measurement across a profile of a small field or something like that in the low dose region, you will kind of bump up against that noise floor of the electronics itself. It's not an absolute dosimeter as defined by the calibration labs. So you do require a reference dose. You have to cross-calibrate it if you want output in terms of dose. It does need an occasional recalibration as the plastic ages. It yellows slightly. I think we've all seen old PMMA phantoms that have been dosed significantly, and you can see a yellow gradient throughout it from the dose that it's received. That happens within the scintillation fiber, the optical transfer fiber, and so that changes the shape of the spectrum that is transmitted through that fiber to the optical detection in the device itself. And so it does occasionally need recalibration. You lose about maybe 2%. Yeah, it's 2% of the signal per kilogray of dose that's delivered. So it's not super rapid for normal uses, but it is something to be aware of as you're stepping into the world of simulation detectors. We've also found, and I put this as a limitation, that it's uncharted territory for a lot of users. So it does take a little bit of getting used to when you're trying to troubleshoot why your measurements may not line up exactly with what you expected. It's not the same ion chamber you've always been using. There are a few other factors at play here in terms of the Cherenkov or the light transfer. So it's not intuitive at first to many users, but I will say that once you get used to using scintillators, they are quite fun to use. The W2 was our second generation device after we'd really established that the W1 did what we expected it to. The next step, of course, was to try and improve the signal to noise ratio and allow it to be used with a scanning water tank. And so the W2 has dedicated optics and electronics unit called the Max SD. And putting all of that together rather than having long cables to go from the optics on the W1 to a dual channel electrometer, we were able to have this be a user replaceable fiber. We could have multiple detector sizes then at the end of the fiber. So there are 1x1 and 1x3 scintillators available with the Max SD. The 1x3 is actually quite useful for a couple of reasons. One is you get 3 times the signal from it, so your signal to noise is quite nice on that one. But also it gives you that direct comparison, apples to apples with the W1, if you're looking at any publications from that. The Max SD allows you to do the Cherenkov correction directly with that unit, as well as individual point measurements with the Max SD. But it can also do a very fast Cherenkov correction. Every 10 millisecond integration, it will apply the Cherenkov correction, and it can convert that corrected value to a single output current, an analog output that can be sent then to your water tank scanning electrometer if you're scanning with the W2. So this is really an advantage in terms of being able to really characterize your small fields, look at those small field profiles or PDDs. The scintillator mounts in your water tank. There's an adapter sleeve that allows you to use your standard chamber holder in your tank. It can accommodate both the standard 8 millimeter diameter chamber holders and 7 millimeter diameter. The fiber then, the optical fiber is then plugged into the input of the Max SD. And then there's an output, triax output from the Max SD that goes into your water tank scanning electrometer. So really this just acts as a pass-through intermediary between the detector and the water tank electrometer. And to the water tank, this looks no different from a diode. You don't apply bias to it, but when the detector is irradiated, you get a measured signal. Let's see. Whoops, it looked like there was a question and now I'm having problems getting it open. There we go. Raquel asked, when we configure the Cherenkov correction, does it work for all field sizes or do we have to repeat for each field size? It works for all field sizes. The reason for the Cherenkov correction, the way it's done is so that whatever amount of stem is being irradiated, we can account for that signal properly. So you really only need to do the CLR characterization measurements at a single field size, and then you can use that value at other field sizes. And to the second question that Raquel asked about the scintillator being used with other tanks, yes, you can certainly use it with tanks that are not standard imaging tanks. The images on the right side here that I'm showing you is a holder that we made for the water tank for slightly smaller field or water tank use, a water tank process for doing your CLR characterization measurements. So your minimum fiber configuration would be here with the fiber coming straight out, and a maximum fiber configuration with the fiber wrapped around. And this is being held in the standard imaging water tank. It's very easy to switch between a vertical diode holder and a horizontal bracket for the scanning chamber like this. So this is being held with a vertical post in a vertical diode holder. If your tank doesn't have that, if you're not using an SI tank, or you don't have a holder that will accommodate a vertically oriented diode, you can use a rectangular field method with the W2 setup in this configuration, where really you would have the rectangular field oriented long axis along the axis of the W2 for the maximum fiber configuration, and then rotate your collimator and have it oriented then perpendicular to the W2 axis to get that minimum fiber configuration. Okay. So with the W2, we've managed to keep all of the strengths of the W1. It's the same optical fiber. I somehow managed not to put it on here as well. It can be used in MR Linac because there aren't any ferromagnetic parts in that fiber at all. You just have to keep the max SD outside the 5 Gauss line in order not to bother the electronics with the magnetic field. But we've managed to eliminate a couple of the limitations of the W1 while keeping all of the strengths and potentially even adding to it. It does still have the same properties of the scintillator. It requires that reference dose. It requires that occasional recalibration as you're using it. So the old standard finally working properly. I promised you a little data about that. The A26 has been around for a while now, but it was designed as a result of Jessica Miller's PhD thesis investigation at UW-Madison. She was looking at all of the micro-ion chambers that were on the market at the time. All of them exhibited a strange behavior in terms of recombination or ion polarity. So the red plot here shows applied voltage, and if you're applying a negative voltage, you're collecting positive charges. The chamber might behave this way, whereas if you switch polarity, it behaved very differently. So for quite some time, and I think, well, I should say even now, the calibration labs recommend that if you're using a micro chamber, you should not bother with applying the polarity correction, because it's kind of a nonsensical polarity correction. It doesn't really represent recombination the way it does with a farmer chamber. You should use it at the polarity that it was characterized at or calibrated at, so that you're consistent with that measurement with that recombination. With the A26, you can certainly apply a polarity correction. It has been designed in such a way that we do not see that sort of behavior with this one. Its electric field lines behave properly, so that you're not actually changing the shape of your collection volume. That was really at the heart of it. So as we were designing this, we were looking at chamber spot size. How small can we make this detector and have it have this uniform response? We were looking at making sure that the spot size of the chamber was spherical. That's again that region that's encompassed by the detector, so that it didn't matter if you were scanning one way versus the other or measuring arcs at different angles. You would be looking at the same shape for the volume integration. The chamber volume, of course, affects the signal magnitude. So we're looking at signal to noise ratio and whether that would be sufficient for the measurements. The volume then ended up for the A26 being almost exactly double what we have for the A16, which has a metal central electrode. So you get quite a bit more signal, which makes a nice signal to noise ratio. Although it is still a small chamber, you still are looking at small signals from it. But we only had to increase the spot size by less than 1 millimeter. So you're really not compromising very much on the size of the fields, the small fields that you can investigate. So strengths of that A26 is that it is really the only reference class ion chamber that is this small. It's the only micro chamber that fits those categories. Its spot size is independent of orientation. And ion chambers are very familiar technology for most physicists. Limitation of the ion chamber is that it does require corrections to account for the air volume, as do all ion chambers, just because you have decreased density there where the air volume is, and so it will require those corrections. If you're making measurements in small fields, especially with small signals, you really need a highly accurate electrometer that can handle those small signals. So we have two that I'd like to bring up today. The Max 4000 Plus really is the workhorse. It's a very robust single channel reference class electrometer. It has been on the market for quite some time, has very nice range and resolution for the charge and the rate measurements. And it is a favorite of a lot of people. The Supermax is our high-end electrometer, so it's a dual-channel electrometer with a touchscreen interface. Each of the channels can be managed independently for their bias. It has a very short warm-up time. So that is also very useful if you're doing 1D tank scans and you want to use a reference detector. You can use our electrometer to run the two ion chambers and work with our 1D software, DoseView software, as you're doing those scans, or if you're taking ratios in order to look at energies or output in different places. There's a question about the smallest field size for the small ion chamber. That really depends on the correction factors that you're using. So just because you can put a field around an ion chamber that fits this field there, doesn't mean that you'll get an accurate measurement. You really do need to correct for that lack of lateral scatter. The rule of thumb is usually that your field needs to be, now I'm going to quote it wrong. I think 2.5 times the width of your ion chamber. That's what the AAPM recommends. I think IEA as well, although that's a good question. So it really depends on the size of, or the profiles that you're looking at, and just how much perturbation you are introducing that you're comfortable correcting for in those small fields. So on to 2D detectors. We have our QSA Stereo Tracker imaging panel. Film is used in a lot of our phantoms. I'm not really going to touch on that much here, but I do want to kind of showcase the stereo checker a bit because it has a lot of advantages in this small field realm. It's currently primarily designed for use with the CyberKnife system. There was a pretty strong need there for much more robust and fast QA because of the length of time that was required, is required if you're using film for all of the daily measurements that you're supposed to be doing. We found in talking with a lot of users that they didn't have the time to do the several hours worth of QA every day. And therefore, a lot of the QA was not being done quite as frequently as was recommended. So this really makes it possible to do everything that you really feel you need to do, as well as the things that are recommended in order to be confident that you're treating your small fields well. So it has fiducials in the housing of the imaging panel, so it gives you the ability for a very fast and consistent setup because you can use your imaging alignment system. You don't have to, for CyberKnife, you don't have to put the robot into the manual manipulation mode or physics mode. You can treat in the regular treatment mode. You don't have to attach the bird cage or other positioning systems to the collimator housing. So that again makes it a lot faster. The images are collected at very high speed and high resolution. We're looking at 200 microns for the pixel size. And the system is really designed to be used by either physicists or therapists. So the therapist can run the morning QA with the device, and it is a portable and compact size. So some of the QA tasks that are required for the CyberKnife, there's Iris QA, the MLC garden fence, picket fence, the AQA test, which we call Panda in ours, and then output. With film and an ion chamber, it takes quite a bit of time each day or monthly if you're doing these monthly ones. But with the stereo checker, you're reduced to 15 minutes for a daily. You could do all of it daily and be done within a half an hour. So a little bit about the Iris QA. You can look at every one of the iris sizes in one delivery. Since we're collecting the images live with the panel, it can collect and perform the analysis and get you your results very quickly. I see I neglected to update screenshots. There should be new screenshots here for the updated version of the software, but it works quite seamlessly in terms of you push the button, do your delivery, and it does all the analysis for you. You get your metrics for flatness, field width, penumbra, all of the things that Accuray recommends there. The Panda test, which replaces the AQA test, if you're familiar with that, has you create a field where your target center is actually below the plane where we're measuring. So if you do 5 fields from these different angles, all targeting that center alignment point, the slice that we get through here is very sensitive to the positioning and the angle of those beams. And so if they're too close together, or if the position of your panel is off, you can tell based on the spacing or the relative size and shape of those beams. So this Panda test is capable of detecting 1/10 of a millimeter translational offset in your beam. We can do the garden fence test, which is the recommended one from Accuray, in about 5 minutes for your MLC QA, and give quantitative results of the leaf positioning. And there we're capable of detecting leaf variations of 0.2 of a millimeter. The other nice thing as we're going through these tests is once you set up the panel, you can just leave it there. It's one setup and you can deliver all of the tests to it, even as you change between cones or iris or MLC. We can also do a picket fence test, although the garden fence is the one that was recommended. And this moves your picket fence test from a qualitative look at the film and see what looks brighter, what looks dimmer in the overlap of the MLC leaf positions to an actual quantitative analysis. So on to phantoms, small field phantoms. I'll talk about our Lucy phantom first. This is kind of the premier, well, kind of, it is the premier stereotactic phantom with extremely tight tolerances in order to really allow you to verify that you're meeting the tolerance needs of your stereotactic program. I should say we have frames if people are still using frames for the different setup. Or the BrainLab maskless system, we have a very sleek way here of having this mount to the mask holder. There's also the dedicated holder for the Lucy Phantom that has a positioning base that fits on a Sivco lock bar, so it can be repeatedly positioned just on your couch as well. It's really designed for the full end-to-end testing, so scan, plan, treat, and verify. These are some of the CT scanning inserts. We have fiduciary markers, image distortion grid, different densities, and then targets, and there's a BB in this one, irregular shaped and regular shaped targets. Same thing for MRI. We have a larger distortion grid, as well as localization markers that align perfectly well. I mean, within that very tight tolerance with the CT markers. MR signal generator, and then matching target structures, exact same shapes as the ones with CT, although this is the same insert, so you can use the same insert for both. As you're doing your planning, you can check, you can do CT Fusion if you're doing cone beam versus your planning CT, CTMR Fusion, create target plans, aligning with markers as well here. Plan and treat to the various targets and measure with either ion chamber. When you verify, ion chamber locked into place here so that it doesn't slip out. If any of you have had problems with phantoms in the past where you think you've put your chamber in all the way and then you walk out of the room, you discover that it's kind of slid its way out. That's the reason for this locking piece here. We can drill inserts for an array of chambers, can do the film measurements if you'd prefer that. And then orientation can be either end on here or from any of the sides for the chamber detector with rotation demarcated, so you can get that set up easily in the different orientations. We also have a Multimets phantom, target and avoidance structures, multiple film stack, different tools there to help you really feel confident in your stereotactic program and your small field deliveries. We have end-to-end, well, you can do more end-to-end tests. We have a hidden fiducial marker that can be used for targeting or for planning that would be right at the location of the ion chamber if you were using an ion chamber for your QA. Or of course the standard Winston-Lutz pointer. You can do either the hidden Winston-Lutz or the viewable standard Winston-Lutz. The stereotactic dose verification phantom, sometimes called SDVP or baby blue, is a wonderfully versatile little phantom that's designed a little bit more for the SBRT, although you can use it as you're getting ready for stereotactic radiotherapy as well. There are a number of configurations available for that with scribe marks and fiducials included in the phantom so that you can use imaging alignment. The chamber plug can be drilled for a wide array of chamber sizes or detectors. You could even get it for the W1, which has been fun, or W2. Different configurations. I'll just kind of fly through. I know you can look up a little more info on our website, but for film measurements or ion chamber measurements, there's the same target and avoidance structures that we've got for Lucy, along with some different densities and air pockets, so you can do some imaging verification there as well. The one I like the best, though, I have to admit, is the heterogeneity slabs, where we have lung equivalent materials with the chamber plug acting as a lung tumor, essentially right in the middle of the lung equivalent material. So this is an excellent way to commission or validate your SBRT calculations with your TPS, and in fact was designed for the Monte Carlo commissioning with the CyberKnife in order to validate that was really performing the calculations as expected as you're getting your system commissioned. It really does test your system in one of the toughest configurations that the TPS has to deal with. You can also pair it with the respiratory gating platform in order to really look at the full QA of your SBRT program, lung SBRT. So that's what I had. Sorry for flying through the products at the end, but I didn't want to quit our discussion on small fields without mentioning some of those other important tools. I'm happy to look at more questions if you've got more questions about any of that, or if you'd like to visit our website, standardimaging.com, or contact your sales representative at sales@standardimaging.com. We'd love to continue that conversation further as well.